So we are going to just continue here to. So our topic today is how symmetries come into the language of quantum mechanics. How symmetries are, as an idea, is very general, not only in physics as mathematics, and intuitionally it's somehow rooted in human consciousness that you are more interested in the symmetrical things. So whether symmetry is a construct mathematically we need as a human mind you want to just minimize the what are the minimum parameters by which you can describe a certain system, physical system, or in our case quantum mechanical system. So symmetry, so it's an idea whether our constructions, whether our need to find symmetric configurations or symmetry in nature means that nature is ultimate sense symmetric or not. So this is a very debatable thing. It leads to questions may not be necessarily physics, but on the borderline of physics and philosophy. But in today's class, what symmetry? So if you just go through Weinberg, the short of statements is that classically the quantum mechanical understanding was taken from how we departed from the classical way of looking at things. So there is a particular classical to quantum quantum correspondence. So historically, so there can be two ways. So either historically you can study classical mechanics as how we depart from the way we study classical mechanics, and maybe the algebra, the part of Poisson bracket algebra, and how we can make the equations of motion, how they get translated, how they get modified when we try to study quantum mechanical systems, where we have a particular way of looking at things. Or this is the one is the historical way, and the other is that historically how classical went to quantum, or other is that if you take quantum mechanics as a fundamental theory, but how we arrive as classical mechanics as an symmetrical, as a limiting case of quantum mechanics. So the point Weinberg, if you study Weinberg, so he wants us to, he just, so you can do away. So there is another third alternate way of just looking at this thing, and that's the how we can take the arguments of symmetry and have a correspondence of symmetry with the quantum mechanical principles. So symmetry as such is that if you have some operations or certain set of operations which will leave a given state invariant. So symmetry as such becomes more important. So it's not necessarily we will take a recourse to this classical to quantum correspondence. So we can go and take recourse to some symmetric principles and just explain, or we can mathematically formulate quantum mechanical principles accordingly. So in our earlier understanding of classical mechanics also, if we have this Noether's theorem that every conservation law has symmetry associated with it, but the symmetry as such can be a very general principle. It can have a classical symmetry, it can also have a quantum mechanical symmetry. But if you take symmetry as a fundamental thing rather than going for this the traditional way, so we can say that For example, whether it's translational symmetry or whether it's rotational symmetry or different sort of symmetries. Maybe in the symmetries, yeah, that's it. For example, so symmetry. So. So symmetry. So one important thing is that symmetry. Once we invoke symmetry, it doesn't mean that once we change a given physical or quantum mechanical system to its alternate system using of symmetry. The change of symmetries, the change of this, for example, new states. For new states, new states or the symmetry. Sorry, the symmetry transformations. If we have a given quantum mechanical state and we are going to translate it or transform it rotationally or translationally, so this given state, its translation, rotation, transformation, whatever you might call it, to a given state via symmetry doesn't mean that it will not change physical states. So, so if you translate a given system, quantum mechanical system via translation, rotation, or we are going to transform it via these two operations, by virtue of symmetry, doesn't mean that the physical system doesn't change. It only means that the laws of nature, which were applied prior the state here, the quantum mechanical state, they will also apply to the new state which after this transformation operation which were imposing on the system, on the quantum mechanical system. Only thing is that there might be some phase factor or so which we'll see how we just translate it. So they will be observed to satisfy same laws as that of same laws of nature as that of old states. So in a particular symmetry transformation must not mean that symmetry transformation must not mean that must not change the transition property, change the transition probabilities. So what do you mean by that? So it means that, so if you remember, we have been using the state psi, and that state psi was basically represented by normalized Hilbert space with a particular inner product which had a particular property of being a symmetric conjugate. So what? So state, if state is represented by, if this quantum mechanical state is represented by normalized Hilbert state vector psi, and now we are going to perform measurement on this thing. If we are going to perform measurement, then measurement on the set of measurement we are performed on the set of observables represented by commuting Hermitian operators. So measurement, we are going to have a measurement on set of observables represented by commuting Hermitian operators. That's fine. we perform major set of observables represent, so that's fine. So which puts a system of from one complete states represented by orthonormal state vectors such that the probability, so if you have if you define a state and the measurements are represented by commute information operators, so what we will say that the complete set of states represented by orthonormal vectors phi I, and the probability of finding psi goes to phi I, which means that, so we are going to have it, the probability is moved by the inner product square out. So if it is that way, so if I say this means that symmetry transformations must leave this psi phi modulus of this psi phi square invariant. So this is the thing. So it must leave it invariant. So now, if you if we want to say that if we want to invoke how we have the unitary operators which are acting on these states psi, another way of stating, and how we have the unitarity, where u dagger u is 1 or u inverse u is 1. So that property, how it comes handy in just stating it, the same thing, is that symmetry transformation takes general state vectors psi into other state vectors u psi, where u is a linear operator. So satisfying conditions of unitarity, so which means u dagger u is 1 or u inverse u is 1. That's it. So if we want to state it in terms of this linearity thing, if you want to have a how we can have some simple properties which we just invoke them. For example, for the condition of unitarity, we have where u is a linear operator which is satisfying unitarity, then for any two state vectors psi, for any two state vectors psi and phi, we can say that u of psi should be phi of psi. So this is one. So we can get the state back. Or if we have an adjoint operator, if you recall adjoint operator, so you can still write it u phi, u psi in terms of phi. You can write it u dagger u psi. You just recall the properties. Or the operation relation can also be written as this. Now, if we limit ourselves to the symmetry properties of maybe rotations as well as translations. For example, in case of rotations, if we have an angle theta, you can You can also invoke not only these are not of this unitarity operators or sort of also so inverse operators. So you can have u dagger u is equal to 1 or u inverse u is 1. So you have an inverse operation. So if you have a rotational symmetry of theta angles in the inverse direction minus theta, it will come back where you started. So that's it. So it will flip the thing configuration back to its initial state. So if the symmetry transformation of rotating along some angle theta, so it will flip it. If you have minus theta, it will flip it back. So if the symmetry transformation is represented by linear unitary operator, then psi goes to u psi. And inverse operator. So inverse operator means u inverse will let u side to go to psi, है ना? So you operate so psi goes to u side, this linear operator. If you have an inverse operator u inverse on u side, it will get psi back. It will get psi back. So that's it. And from this one is u dagger, so you can have u inverse u is also 1. And if you have subsequent operations of inverse, then so u inverse u of inverse will be equivalent to, it will be u inverse of 1, u inverse is 1. So inverse of inverse is u, so it will again be u inverse u is 1. Or because u inverse of u inverse will be, so u inverse of yes, that's fine. So I have just skipped this step, so you can see it, u inverse u is 1. Or if we acting on this right hand side of u inverse, or from this you can have this property that u dagger is equivalent to, so if u inverse is u, so u inverse is u inverse is u, so if you substitute it here, so you can say that u dagger is u inverse. So this is it. These are simple things how we can have this unitary operator, and it's how we can have its adjoint representation or inverse, how the inverse and the invoking of inverse, which is sort of inverse symmetry operation, which is attached to this thing, can be seen. So now the important thing which comes is that is how you can say that so then the point is that is this the only symmetry transformation which can act on, or the question is only symmetric transformations can act on physical states? So this is the question. So it's not, so symmetry as such is a very broad thing. So there can be some classical or quantum mechanical operations, or here we are interested in quantum mechanics operations, symmetric operations. But not all quantum mechanical operations can have symmetric configurations. So if, for example, the question, if you want to zero in, or is the, so maybe that's a different thing. So, but here, what is the question is whether symmetric transformations can only way is that only there can be only a symmetric way where we can act on physical states. So is it a restriction that symmetry as an operation is only to be yes, once we are making translations or rotations on the quantum mechanical states, only symmetric things are possible. So this is a question. So the question is, but in the quantum mechanical system, once we define a Hilbert space, it's not a particular state. It's whole range of those states which can exist in the Hilbert space, and how we define the basis states, whether it's an orthonormal states or orthogonal states, and the corresponding map once we take a state psi goes to phi by some operation. So there can be whole class of states which will map those orthogonal or ortho states from configuration state A prior to operators acting upon them and after operators are acting upon them. So if the map so the point is that so quantum mechanical state is a physical state not represented by specific individualized normalized vector, but a ray of it's represented by a ray of whole class of normalized vectors that differ from one another only by phase vectors. Phase vectors. So we have no so array of whole class of normalized vectors that differ from one another by only phase vectors. So numerical factors with modulo unity. So we cannot. So this is a restriction. It's not. We cannot assume that all the symmetric configurations will map to Hilbert spaces in some restrictive way. So we'll say the whole rays of. So the proper statement will be that so symmetry transformations maps rays. So we are using the way here rays into rays. So rays may be a specific class of unitary operators which may be mapped those rays into the corresponding configuration of that rays. So it's not that you are mapping a particular thing into a general thing. You are mapping a particular state, and after the application of operators, those states map into the particular states, which we say in rays. We identify them as rays rather than as vectors. And they might differ from each other by a certain phase factor. So that's it. So even though the symmetric operation will leave the state not changed in that sense, in the physical sense, but there will be some phase factor by which the original state may differ from a state which has a change under the set of operations. Yes, the phase factor is there. So if psi and phi are states belonging to rays representing two different physical states. So the symmetry transformation takes two rays into two other rays. So if it's sine phi, so sine phi goes to psi prime phi prime, such that psi phi, so which we have previously also square, it should go to psi prime phi prime square. So they might, so these psi-phi square, they might differ from each other by certain arbitrary phases. And that's it. So normally those phases are represented by scale. So there can be there's a particular theorem which was stated by Wigner in the beginning of historical development of quantum. In the time first, these how the symmetry principles were invoked in this quantum mechanical understanding or representation theory or group theory. So there's a history to it, but here we are going to say that there's a physicist named Eugene Wigner who has given us conditions or ways that there, what are the ways by which we can go to these symmetric transformation. What are the sort of operations? What are the, so there can, according to that theorem, so we only stated. So there are just two ways uh, and this condition is satisfied. This condition of psi pi psi prime phi prime square is satisfied. So what are the conditions? So when, as far as the phases are concerned, you said that there can be arbitrary phases by which they might differ from the original state when a certain operator is applied upon them to the which maps to the corresponding states. So the conditions which might which by which those phases are chosen, so that the effect of symmetric transformations on a state vector psi goes to psi of u of psi, where u is a linear unitary operator satisfying the condition which we have seen, u phi u psi. So we can have it as u psi, phi psi. So unitary operator on phi, unitary operator on psi should not change the original commutation. Can go from this to this and vice versa. So this is one condition. So this we have seen it. And the other possibility, which might be more important, is that U is anti-linear and anti-unitary. So what do you mean by that? So if you have a certain familiarity with how we define linear algebra and linearity properties and anti-linear properties in those finite dimensional vector spaces, we can enumerate the properties of how we can define linearity as an operation and anti-linearity as an operation. So if U is now in the first case, so you can see it, but if U is anti-linear or and anti-unitary, then we assume that, or it should, so it's a theorem sort of, if you assume, but you can have proof of it, is psi plus alpha prime psi prime. So this anti-unitary operator, or it's an anti-linear configuration, then this should, so for this thing it should be linearity preserving, or it should be anti-linearity or anti-unitary. In the first case it's unitary, then the two cases should satisfy. Now and u phi u psi is phi of psi star. So note that the antilinear operations cannot be linear. That's fine, because it is because if it were that, then we have so linear operations and antilinear operations cannot be same, are not synonymous, in the sense that if we apply that, for example, in a particular case, you can see it. So we leave it as an exercise. You can see that you cannot show, or if it's linear is equivalent to antilinear, this means we can justify this u phi u alpha psi. So that this is fine, but it should be equivalent to what? Phi alpha psi star is equivalent to alpha star u phi u alpha. But it may not be, it's not true for the complex case. So you can take it as an exercise in homework to show that this cannot be equal to this for complex cases. It will lead to. So for antilinear operators, the definition of adjoint, so we have to change the definition of adjoint. So it's how we just have a formalism where you can sometimes change some definitions. For example, in a product spaces, sometimes so we can just like mathematicians do, physicists also, because we are formulating quantum mechanical theory. So we are going to change, alter some assumptions to suit what we want to formulate. So if you change the definition of adjoint such that u dagger phi is equivalent to phi u psi. So then equation 34.3. So then if you just change this definition, that so this is a sort of thing. So if you just change the definition of this u dagger phi, this operator like this, then we can say this u dagger u is 1. You can, so it's under exercise. Whether once you change this to this definition to this u dagger u should hold, or you can check it here also. So u dagger u holds. You can have u, then u dagger. So this is the configuration can be 1. So that's it. So this means that symmetric operations. So this means that probability of when psi goes to phi under some unitary transformation, it will leave this thing under not now a unitary transformation, under anti-unitary transformation, which is anti-unitary transformation. It will again leave this phases in this invariant states invariant. So we are invariant. So again, what we are going to say, we suppose that the symmetry transformation takes generalized state to another state vectors and use the linear vector operator satisfying the condition of unity. Then for any state vectors, find psi, u phi, u psi, goes to phi of psi, and Adjoint of the operator is defined as u phi u psi goes to phi of so u dagger, so we can also have u dagger u phi psi, u dagger u phi psi. Sorry, not phi psi. And again u dagger u is 1. So again we are going to use the previous exercise where we said that u dagger is equal to u inverse, and u inverse of inverse is 1, and using that thing, so we can say u inverse u is 1, or inverse of this u is 1, or this means u inverse is u. And again we are going to so the same of exercise we did it for this unitary transformation. We can just or at the end we'll have u dagger is equal to u inverse. So the way you can do it for the unitary transformation, you can do its antilinear and antiunitary having this property, and you can use these properties to show this unitarity statement. Sorry. Oh, sorry. I just forgot. Sorry. Maybe this is not correct. This is not correct. This is not correct. I just flipped the page back. So we can say that probability of so you can say that. So if it is this way, so that's it. So the other thing is that you can also have an operator 1 which will have a trivial symmetry. So it has nothing to do with state vectors, and so if u1 and u2 are symmetry operations, so does the way we defined yesterday. If you remember, we had a particular that's known as dyad, or two operators who work in unison. So in the same way, you can have an operator u1, u2, which represent symmetry operations. Symmetry, rather transformations. So if u1, u2 can be defined, so you can have existence of inverses in both of them, u1, u2, and they will form a sort of group. So what we can do is that the special class of transformation, symmetries represented by linear operators for which u is or t. So we can have a symmetry such that we can define symmetry like this. So maybe in mathematics, once we study Lie groups, Lie algebras, so things will become more clearer when we have a rigorous thing. But here we can say if we have a special class of symmetries such that the symmetry operator is defined like this, and epsilon is an infinitesimal number, and epsilon is this epsilon is and epsilon is an t is an epsilon independent operator, then we can have this u dagger loop. So we can just see the unitary condition u dagger is 1. We can have 1 minus epsilon this t 1 minus epsilon t dagger. plus, so it's u dagger u. The u is this one plus iota epsilon t plus o. So these are higher order terms. They should come to 1. So for unitarity conditions, t dagger is t. So this is an epsilon dependent unitary this adjoint operator t. So t dagger t is t. So now what we can do is that, so in the Hermitian operators naturally arise in presence of. So if you take epsilon to be theta by n, where theta is some n independent parameter, and for the symmetry transformation n times, let n go to infinity, so this will somehow simplify as t by n as exponential of iota theta t. So you can define it like as this theta. So now one important thing is that which we have to see here is that so to see Hermitian operators t, so when both sides of the equation act on the eigenvector iota t, both sides of they will act on the eigenvector iota t, this and this. So t can be, so we can replace eigenstate by the eigenvector which we have been doing. So what? These eigenvectors, it is true in general. So the operator, this operator is known as generator of the symmetry. So this operator is known as the generator of the symmetry. So we can have an operator, we can define an operator modulo these conditions which will generate some symmetry. Modulo some phase vector where the value of n can be. So you can generate symmetry from a particular definition operator. Now the important point is that which is known as the generator of the symmetry. So we can generate an operator, we can have an operator which a particular way of defining it, where t and t or eigenstates are replaced by eigenvectors. So if you have this configuration, you can generate symmetry from a particular generation from a particular definition of operator, which corresponds to as if we are generating a symmetry by the application of dot operator modulo these when n tends to infinity. So if it is that way, the next important question is, so it's an important observation. So many, if not all operators representing observables in quantum mechanics are generators of symmetry. So this is previously also said that you do all symmetric operations exhaust the quantum mechanics. So symmetry as such is a general idea, it's a more general statement, but many, if not all, so this is important, many if not all, so there are a good number of operators which can be represented by observables which have a quantum mechanical correspondence, which can be taken, which are the generators of the symmetry. So there can be some operators which can be identified as quantum mechanical operators, and which have a certain symmetric way of generating them, observables in quantum mechanics. So there is a correspondence. So now under symmetry operations, psi goes to, so it's a unitary operator simply, or there can also be the anti-unitary and anti-linear configuration defined in a particular way. Still, you can generate symmetries. So under symmetry, the psi goes, the expectation value of any observable A is subject to the transformation. A is subject to the transformation. Subject to the transformation. A is subject to the transformation. Psi of A psi goes to u psi A u psi. That's fine. Or if we have u inverse here, it will be psi. It will be A u inverse u. A, so it will be psi u inverse u is 1. It's u inverse A u psi. So you can define it like this. So or A goes to u inverse AU. So u inverse u is 1, so this is, you can see it. So in the same way, we can call these sorts of transformations as similarity transformations. Similarity transformations are transformations which preserve some algebraic relations. In the simplest case, for example, we can have u inverse AU cross, if we have two operators A, which are, so, and another operator is B, having these properties, so we can have u inverse, so you can have sort of commutative, so sort of this is this, you can have u inverse u outside or AB inside, so you can have this. Or if you, for the case of if you have an addition, u inverse for u inverse AU plus u inverse BU. So you can again have it A plus B, so u inverse A plus B into this. You can have these sort of thing. So also symmetry transformations do not change the eigenvalues of the operators. That's fine. If psi is an eigenvector of A, the eigenvalue A. So u inverse psi is the eigenvector of u inverse AU or u inverse A plus B. Again, if you want to go to this previous definition of this thing, say that operator A is transformed to A minus iota epsilon T. So this is a commutator which we have introduced. Commutator. So once we study Lie algebra, is a proper way of how we can see those, how we can represent them. So they are, these are basically infinitesimal symmetric transformation on, they are symmetric infinitesimal transformation on commutation relations of the symmetry generator, we can say. So and the commutations relations describe the nature of, they will reflect the nature of symmetry group. So this is today's lecture on how symmetries and symmetric operators, how to generate those operators vis-a-vis the observables, and the role of symmetry in the quantum mechanical operators. So it's an interesting thing. So we'll stop.